All right, class. The next thing we're going to talk about is thermochemistry. So thermochemistry is when we have delta H of a reaction. Now, what does that mean? That means when heat is released or absorbed when reaction happens. So how much heat is released or absorbed when reaction happens, reaction occurs. That's delta H of a reaction. How much heat is released or absorbed when a reaction is happening. That's delta H of a reaction. Now, if you want to be fancy, instead of saying delta H of reaction to impress someone, you can also say enthalpy. That makes you sound really fancy, huh? You can also say enthalpy. So enthalpy is basically enthalpy change. Enthalpy change is basically what it is delta H of a reaction, how much heat is released or absorbed when reaction occurs. Okay, now let's write a reaction out here. Let's say I have H2O gas and it goes into H2 gas plus half O2 gas. This is my reaction, and every reaction is going to have a delta H, right? This one is 242 kilojoules of energy because every reaction of heat is released or absorbed when a reaction is happening. That's an enthalpy change. That's the delta H of the reaction. So, and then this is the number for this reaction over here. That's the delta H of this reaction. Now, what does this number mean? So here's what this number means. I'm going to give you like a non-chemistry example. Let's say you demolish a house and you build a brand new house, and that's going to cost you $250. Okay, so you demolish a house and you build a brand new house that's going to cost you $250,000, and then you sell the house for $400,000. Okay, so you demolish a house and you build a brand new house for $250,000. That's how much it cost you. And you sold the house for $400,000. What is your net profit? Your net profit is $150,000, right? That's exactly what delta H of a reaction is. What is the net profit? Because it requires energy to break bond. It's going to require you energy to break bond. But you gain energy. You gain energy when you make bond, okay? So I'm going to write this down. So it costs energy to break bonds. Remember that. You have to put in energy to break all those covalent bonds, right? But you gain energy. We gain energy when you form bonds, when you make bonds. When new bonds are made, you gain energy. Okay, so cost energy to break bond, gain energy to make new bonds, and basically your net profit is what? Your net profit is a delta H of the reaction. Is a delta H of a reaction. If you think about the example I said, 250 to build a house, 400 to sell it. What is my net profit? $150,000. Okay, so hopefully you understand what a delta H is, change of enthalpy for this reaction. Now, I want to give you another reaction, and its reaction is H2 gas plus half O2 gas goes to H2O gas. And what I want you to do, I want you to tell me what is the delta H of this reaction. You can actually know, you can actually do this. What do you think the delta H of this reaction is? Now, the reaction that I gave you over here, and I give you a delta H, is over here. And then this reaction is flipped. Do you guys see that? I have water going to H2 and O2. Now here, this is the opposite. H2 and O2 going to water. So it's exactly pretty much the same reaction, but flipped. What do you think the delta H of a reaction is? Negative 242 kilojoules of energy. So think about it this way. If I'm going to go 2 miles uphill and I want to come back down 2 miles downhill, it's the same distance. I go up 2 miles, I come down 2 miles. It's the same distance, but I'm going to need energy to go up. And I can release energy when I come down, but same number because it's the same distance. That's the thing to think about. Okay. Now, here in this reaction is what? This reaction is endothermic, right? This reaction is endothermic because delta H is positive. Now, what does that mean again, endothermic? It means it requires energy. Now, this reaction is exactly the same reaction, just the opposite. Now, this is an exothermic reaction. You would release energy. Again, another way to think about it, I'm going to go 2 miles uphill and I'm going to come back down 2 miles downhill. I go up, I require energy. I come down, I can release that energy, but it's the same distance. So these are the same equation, just flipped. That means I have to flip the sign. Okay, so far so good. All right. So exothermic and endothermic reaction. So we do a lot of chemical reactions on a daily basis. As you're doing chemical reaction, I want you to be thinking about, okay, is this an exothermic reaction or is this an endothermic reaction? Think about those things. For example, when you drive your car, is that an exothermic reaction or is that an endothermic reaction? What do you think? Driving your car is... So now, don't try this, okay? I don't want you to go and burn your hand and then you're going to get mad at me. Do not try this. But when you drive your car for a while, if you get out of your car and if you touch your engine, even don't touch it, just put your hand on top of your engine. Don't touch it, it's hot. Your car engine is going to be really hot. So when you drive your car after a while, your engine gets really hot. So what do you think? Is this an endothermic reaction or exothermic reaction? Hopefully you're yelling at me, Dad. That's an exothermic reaction because it releases energy to the surrounding, so my engine gets very hot. So think about that. Now, another good example I like to talk about is glow stick. Most of you guys have used glow stick before for New Year's and all that. So glow stick, you break the glow stick and it has pretty lights coming out of it. Is it an exothermic reaction or endothermic reaction? So if you have a glow stick at home, go ahead and then break one. If you do it, you see that the glow stick does not get hot. It does not get hot. Is that an exothermic reaction or endothermic reaction? You're probably going to be wanting to say endothermic because it doesn't get hot. But remember, light is a form of energy. So when you break the glow stick, energy is released in form of light. So it's also an exothermic reaction because light is a form of energy. So energy is released in a form of light. So think about these reactions that you do on a daily basis, that it could be exothermic or endothermic. Okay, which means delta H of a reaction could be minus or could be plus. So far, so good. All right, beautiful. Now that you got the delta H of reaction or change of enthalpy, if you want to be fancy, the next thing we're going to talk about is delta H of formation. Okay. Now again, this triangle means change. You probably know that already. Now H is the enthalpy, right? Is a change in heat. And F is for formation. Okay. And degrees, what does that mean again? That means standard. That means you had standard condition. So, delta H of formation. What is this delta H of formation? I'm actually going to define it for you and then we're going to go over it. So delta H of formation basically is a standard enthalpy of formation. Again, a fancy name for delta H is enthalpy. Here's what it is. Change in enthalpy when 1 mole of a substance at STP, and remember how we had STP, standard temperature and pressure for gases? This is STP for reaction. It's slightly different. STP, standard temperature and pressure for gases, was 1 atm. Here is also 1 atm. And the temperature, if you remember, it was 0 degrees Celsius. But here, actually, because we do reaction at a room temperature, is 25 degrees Celsius, which is the same as 298 Kelvin. So it's slightly different temperature because gases, we do gases at 0, but we do reaction at room temperature. Is formed from its pure element under the same condition. And there's a reason I don't usually write definition, but this one is a good one. I want you to notice. So when something is formed from its pure element, that's really key. When something is formed from its elemental form, that's a delta H of formation. And I will give you an example for you to really understand it, but this is a key. It's formed from its pure element. Now, so I want you to really understand that. I'm going to put up a table now. Alright, so here is my table. So this is a table. I give you the delta H of formation, which the unit is kilojoules per mole, okay, for different compounds. Now, remember what we said. We said delta H of formation is how much energy you need to make something from its elemental form. When you look at this, one thing that should stand out to you is over here. O2 has a delta H of formation that is 0. Carbon has a delta H of formation that is 0. Why do you think that is? Because that's how they exist in nature. I don't need to make them, right? That's how they exist in nature. I don't need to make him. So the delta H of formation is 0. Now, if you look at some of these numbers, some of them are minus, some of them are plus. Now, if you remember, we talked about this briefly, that when the reaction is exothermic, is more favored. Because not only you don't require energy, you end up releasing energy into the surrounding. So the more negative their values are, that means it's more stable. It's going to be easier to make and harder to destroy. Okay? So again, overall, you have to think about the delta H of the formation is overall, you're either going to have a plus endothermic or negative exothermic delta H of the formation. The more negative you are, the more stable you are, because not only you don't require energy, you're releasing some into the surrounding. So this is the delta H of the formation, how much energy you need or you require to make something from its elemental form. And if you already exist in that form, it's going to be 0. Now, let's look at this one for a second to kind of understand this a little more. So CO2, right? How would I make CO2? To make CO2, I would take carbon plus O2 and I would make CO2. That's, again, how do I make it from its elemental form? Carbon, that's how it exists in nature. O2, that's how it exists in nature. I would take two things from the elemental form, that's how they exist in nature, to make carbon dioxide. And that value is this. Is it favored to make carbon dioxide? Yes, because it's exothermic. Is exothermic. Not only you don't require energy, you actually release some energy. Now, here's why it's good to know the delta H of the formation. Because we could calculate the delta H of the reaction based on the delta H of the formation. It would be the sum of delta H of the formation for products minus the sum for delta H of formation for reactants. Now this looks a very weird looking equation. And this means sum. I'm going to make this a lot easier than that. Basically, to figure out the delta H of the reaction is product minus reactant. It's as simple as that. You guys got this down. Product minus reactant. Okay? Now, again, the delta H of the reaction is the net. I need energy to break bonds. I gain energy to make bonds. What is my net profit? Now, let's do a practice problem to make sure you understand how to calculate this. Let's say I have 2 NO gas plus O2 goes to 2 NO2 gas. And what I want to figure out what is the delta H of this reaction. Now, what you need a delta H of formation, right? And I said that is kilojoules per mole usually. So in this table, I give you the NO, which is 90.25. Oxygen, you know, is 0. That's how it exists in nature. And if you look at the table that I just gave you, NO2 is 33.18. Again, these are all kilojoules per mole. Kilojoules per mole. Okay. Now, product minus reactant. This is how you would do this. You would add up all the products together and then add up all the reactant together and you subtract them. Now, let's do this together to see how you would do this. So, my product, I have NO2, which is 33.18 kilojoules per mole. Now remember, it's kilojoules per mole. Oh, it's kilojoules per mole. Now, coefficients are the mole ratio. What is the coefficient here? That means I have 2 moles of that. So you have to multiply it by the coefficient, which are the mole ratio. So the mole can cancel out. That's the only tricky part that you have to remember. And don't forget to multiply by the coefficient. Now, this is my product. I don't have any other product. Minus. Now, let's go to my reactant. My reactant, what do I got? What I got 90.25 kilojoules per mole. I multiplied by 2 moles, right? Again, why did I do that? Right here, the coefficient, to be able to cancel those out. If I do that, so the moles can cancel out, and oxygen is just 0. I'm just going to write it down 2. So product minus reactant. Now, what I end up getting, if you do this, you get oh, don't do that. You get, okay, you get minus 114. What's the unit? Pay attention. The moles cancel out. Now I have kilojoules, minus 114 kilojoules. That's really key for you to get the units down. Not bad, right? Okay, ready to do one more practice problem? Here is the problem. Okay, so what I want to know for this problem, I give you the delta H of the formation. What I want you to calculate the delta H of the reaction. So pause my video and then do this. Now remember what we talked about. We said to figure out the delta H of the reaction is product minus reactant, but don't forget the coefficient. That really matters. Don't forget the moles. That really matters. So let's do it together. My product, and by the way, the phases really matters because they would have different delta H of the formation. Like water gas and water liquid have different delta H of the formation. Pay attention to that. Alrighty. So I have carbon dioxide, which is minus 393.5. I have to multiply it by the coefficient. Don't forget that. Plus, my water is negative 285.8 multiplied by the coefficient, right? Multiplied by don't forget to multiply it by the mole ratio, right? Because the coefficient is on the mole ratio. Because it's kilojoules per mole, so you have to multiply it by mole so the mole can cancel out. So that is all my product. I don't know why that's happening. Now minus, let's look at my reactant. My reactant, I have propane. Again, the coefficient is just 1 and oxygen is 0 because that's how it exists in nature. So product minus reactant. If you do that, what you get is negative 2219.9 kilojoules of energy. That's a delta H of the reaction. And again, it's kilojoules. It's not kilojoules per mole because the moles has already been canceled out. So pay attention to the unit. Okay, so my net profit is what in here? This is a favorable reaction because this is an exothermic reaction. It's an exothermic reaction. And exothermic reaction is good because not only overall it doesn't require any energy, it's going to release energy into the surrounding. So it's my exothermic reaction. All right, nice job. Now next time what we're going to do Hess's law.